So we want to look at transformations and symmetries in quantum mechanics. So in quantum mechanics, the state of our system is described by an element of a Hilbert space, say psi. If we make a transformation on that, so T is some transformation on that state, then we have to end up with another state, an element of our Hilbert space. Now what does it mean that this transformation is a symmetry, this particular kind of transformation? Well, whenever we look at our state psi, if we make some measurement on it, then we'd have to expand it in terms of the eigenstates of that observable. So suppose these UJs are the eigenstates of some observable, then the probabilities of getting each UJ will be given by the mod squared of this. And the mod squared of this is given by the mod squared of the inner product of the two states. Now, the inner product of the two states, if these numbers are not going to change, if these probabilities are not going to change, it means that when this transformation is a symmetry, this inner product must be the same. It can't change. And what that means is that the inner product between any two pairs of states has to be the same under this transformation. And because this is an arbitrary observable, in fact, it has to be any two pairs of states. And because this is an arbitrary state. And that's an incredibly restrictive assumption. And there's a theorem that states that if we have a transformation like this and it obeys this for any pair of states, then this transformation must either be linear and unitary or antilinear and anti-unitary. We've never met antilinear and anti-unitary before, so I'll just introduce those for a second. These have the properties that so basically, rather than preserving the inner product, it gives us the inner product. Notice that these are around the other way. That's phi and psi. This is psi and phi. So it gives a Hermitian conjugate there. And also, if we would normally think for a linear operator, we'd just better take a C number out. Here, if we do that, we actually get the Hermitian conjugate of the C number. And it has a normal distributive property. So this is the definition of an anti-unitary, anti-linear operator. And of course, we know all about linear and unitary operators. And linear and unitary operators preserve the inner product. That's trivial to show. So basically, the two ways it goes is that either the inner product is completely the same, or the inner product is the Hermitian conjugate of itself. And this theorem is known as Bigness Theorem, after the famous Hungarian physicist and mathematician Eugene Paul theorem. So we're looking at transformations because in classical mechanics they were strongly related to symmetries. Now in classical mechanics the kind of symmetries that were important were time-independent continuous symmetries. For something to be a continuous symmetry, then it has to be smoothly deformable from the identity up to some non-trivial transformation. And the identity is a linear and unitary operation, a trivial one. And so all of the operations that we're interested in are actually linear and unitary. So our set of transformations is going to be a set because it needs to be defined by some continuous parameter. In fact, it can be more than one in general. So we might have, say, R continuous parameters. And so if we specify each of these R parameters, then we end up defining a unitary operator, and that unitary operator defines a transformation. About these antilinear and anti-unitary choices, because all the continuous ones are unitary, then all these anti-unitary ones must indeed be discrete, although there are also some unitary discrete transformations as well. So examples of discrete transformations might be something like a parity flip, like if you change all right-handed things to left-handed things, or you reverse the sign of time, or something like that. So those kind of transformations are perfectly valid transformations, but they're not continuous, and therefore they're not of relevance for trying to find conserved quantities. So we'll mainly be dealing with continuous symmetries that are unitary. So a continuous transformation is really a set of unitary operators, and we're going to consider sets of transformations that form groups. Now a group is a very simple mathematical object. It forms of a set of things, and our set is our set of unitary transforms. And it also requires an operation, and the operation is simply the successive application of transformations. So you do one transformation, then you do another, and for us that just means the product of two of these unitary operators. And our group has three simple properties. The first is that if you apply the operation between two elements of the set, you end up with an element of the set. The second is one we've stated already, which is that the identity is a member of the set. And by convention, we set that to be when all the parameters are 0. And the third axiom is that every transformation has to have an inverse in the set. If we add one further axiom, that this unitary transformation changes smoothly in some sense as we change these parameters, then we have an R-parameter Lie group. Lie groups are used in many areas of physics and throughout many areas of mathematics as well. Whenever you have a continuous symmetry of some mathematical object, then a Lie group is a very well-developed way of dealing with that. They were developed by an extremely influential Norwegian mathematician called Sophus Lie. He had a bit of misfortune in 1870 when he was attempting to get out of France during the middle of the Franco-Prussian War, and the French looked through all his notebooks, which are full of algebra and strange coded symbols, and they decided that it was a code book, and therefore he was a Prussian spy. So he went straight to jail and had quite some time there before he was finally gotten freed by his colleagues. And he died at the age of 56 by a vitamin B12 deficiency, effectively, and so he should have really been having more Vegemite, which just explains why he should really be an Australian physicist if he can, rather than a Norwegian mathematician. But his work was extremely influential. Let's try and make this a bit more real and specific by doing a specific example. One of the most common sets of transformations we talked about in classical mechanics was the translation, where we just translate everything across a little bit. So let's set that as something to try cold. So find the form of the translation unitary operator. So you're going to need a unitary operator, which is a function of some length r, and if that's 0, then you don't translate at all. That's the identity. And if that's 1 meter, then you translate 1 meter to the right, say. So see if you can find the form of that unitary.